On Australia's coral reefs, not all danger comes from size, venom, or speed. Some of it comes from certainty. The certainty that a place belongs to someone else and that crossing an invisible boundary will be answered immediately, repeatedly, and without negotiation. The clownfish is a master of that rule. Small, brightly colored, and culturally coded as harmless, it lives inside one of the most aggressively defended micro-territories in the reef ecosystem. When humans drift too close, what follows is not injury in the conventional sense, but escalation, a cascade of stress, movement, and reaction that proves a central theme of wild systems. You do not need lethal force to turn calm into chaos. Clownfish are not wandering reef fish. Their entire world is anchored to a single structure, a host sea anemone. This relationship is not casual. It is one of the tightest mutualistic bonds in marine biology. The anemone provides shelter, its venomous tentacles forming a chemical barrier that most predators cannot cross. The clownfish provides defense, cleaning, nutrient cycling, and increased water circulation around the anemone's tissues. Over evolutionary time, this partnership has become so precise that the fish's survival depends on it entirely. Leave the anemone, and the clownfish becomes just another small, slow, conspicuous reef fish with no real escape plan. That dependency explains the aggression. Unlike many reef fish that can simply flee when threatened, clownfish cannot abandon their territory without catastrophic cost. Eggs are laid on rock surfaces adjacent to the anemone and guarded continuously. Larval success depends on uninterrupted protection, precise oxygenation, and constant vigilance. Any perceived intruder, fish, diver, snorkeler, camera housing, is treated not as a curiosity, but as a potential egg predator or anemone threat. The fish does not assess scale the way humans do. It assesses proximity. If you are close enough to cast a shadow over the anemone, you are close enough to be attacked. This is where the cute animal trap forms. People recognize clownfish instantly. Bright orange, white bands, slow darting movements, everything about them signals safety and familiarity. Snorkelers drift closer for photos, hovering motionless above the anemone, often unaware that they have entered a defensive perimeter measured in centimeters, not meters. The fish responds with the only tool it has: rapid, repeated charges and nips aimed at exposed skin, masks, fins, and wetsuit edges. Individually, these bites are trivial. They break no skin. They carry no venom. But they are relentless. The clownfish does not bluff. It attacks again and again, striking, retreating, and striking once more, each pass driven by the same territorial imperative. The human response is rarely calm. Surprise turns into flinching. Flinching turns into sudden fin kicks or arm movements. And that is where the chain reaction begins. Reef systems are exquisitely sensitive to disturbance. A sudden burst of motion near an anemone does not go unnoticed. Other fish shift position. Cleaner species dart away. Grazers scatter. The water fills with sediment as fins brush coral and sand. What began as a single fish defending a few square centimeters of territory expands into a visible disruption, drawing attention from species that respond not to threat, but to commotion. In reef ecology, movement is information. Rapid, irregular movement often signals feeding events or danger, and both attract interest. For the snorkeler, this shift feels immediate. The calm, floating experience fractures. Breathing becomes faster. Buoyancy control degrades. Awareness narrows. The person begins to move upward or backward quickly, sometimes scraping coral or drifting into other shallow hazards. Nothing has attacked in the dramatic sense, yet the environment has pushed back decisively. A micro-defender has reset the pace of the entire encounter. From the clownfish's perspective, the behavior is entirely rational. Aggression at this scale works because it is persistent, not powerful. The fish does not need to injure a predator. It needs to make presence uncomfortable enough that the intruder leaves. Studies of reef fish territoriality show that small species often display disproportionate aggression because retreat is not an option. Their survival strategy depends on convincing larger animals that crossing the boundary is more trouble than it is worth. Against most reef fish, this works perfectly. Against humans, it works indirectly, by triggering reactions rather than causing harm. The anemone itself plays a role in this escalation. Sea anemones are not passive backdrops. They are sensitive organisms whose tentacles retract or extend based on water flow, contact, and chemical cues. When harassed by repeated movement or contact, an anemone may partially close, reducing oxygen exchange and stressing the tissues that support both partners. The clownfish responds to this stress by increasing defensive behavior, tightening patrol patterns, and escalating attacks. What looks like overreaction is actually feedback between two organisms trying to stabilize a shared system. This makes clownfish aggression a useful contrast within the broader theme of environmental boundaries. Unlike stonefish, stingrays, or sea snakes, the clownfish poses no serious physical threat. Yet it demonstrates the same underlying rule: proximity without permission triggers response. The difference is in scale and consequence, not in principle. Where venom or spines end encounters through pain or injury, the clownfish ends them through disruption. There is a subtle lesson here about how humans interpret risk. We tend to equate danger with lethality, ignoring the ways non-lethal interactions can still cascade into real problems. A startled snorkeler can damage coral, inhale water, panic, or collide with other hazards. In shallow reef environments, those secondary effects matter. Many injuries and reef damages begin not with a predator, but with a moment of surprise that breaks rhythm. Ecologically, clownfish territories are stability nodes. By defending their anemone aggressively, clownfish maintain a predictable microenvironment that benefits multiple species. The anemone thrives. Certain invertebrates shelter nearby. Predation patterns stabilize. Remove that defense, and the local balance shifts. Aggression here is not cruelty, it is maintenance. The fish's willingness to confront animals many times its size is what keeps the system intact. For viewers, this chapter serves as a deliberate pacing reset. After encounters defined by venom, spines, and reflex weapons, the clownfish reminds us that nature does not always escalate through force. Sometimes it escalates through insistence, through repetition, through refusing to yield space. The message is the same, delivered at a different volume. Boundaries exist everywhere, even around things that look friendly. The irony is that people often leave these encounters laughing, telling stories about being attacked by a Nemo. What they rarely recognize is how quickly their calm interaction turned into a scramble, and how little it took to trigger that shift. The clownfish did not change behavior. The human crossed a line they did not know existed. In Australia's reefs, that pattern repeats endlessly across species and scales. Micro-territories defended fiercely, macro-territories enforced silently. The clownfish sits at the small end of that spectrum, but it makes the rule visible. You do not need size to control space. You need commitment. In the end, the clownfish is not dangerous. It is instructive. It shows how tightly tuned reef systems are, how little tolerance they have for intrusion, and how quickly harmless curiosity can ripple outward into stress and disorder. Cross a line, any line, and nature responds. Sometimes with venom, sometimes with spines, sometimes with a tiny fish that refuses to back down, and in doing so proves that even the smallest defender can rewrite the rhythm of the entire reef. The green sea turtle carries an aura of safety with it. Its movement is slow, unhurried, almost ceremonial, as if time itself loosens around its shell. In shallow Australian reefs, snorkelers often drift alongside these animals with a sense of calm that borders on reverence. Nothing about a turtle suggests danger. Its beak is blunt. Its eyes are dark and placid. Its flippers beat the water in long, effortless arcs. And yet, this is exactly where the illusion forms. Not because the turtle is dangerous, but because the environment it moves through is anything but benign. To understand why shallow reefs around turtles are high-risk spaces, you have to stop thinking in terms of individual animals and start thinking in terms of traffic. Green sea turtles do not wander randomly. Their size, oxygen needs, and energy economy force them into routines. They move along repeated paths between feeding grounds, resting sites, and the surface, carving invisible lanes through the reef that are used again and again, sometimes for decades. These are not trails in the physical sense, but behavioral corridors shaped by bathymetry, current flow, predator avoidance, and memory. At the surface, these lanes become especially narrow. Unlike fish, turtles cannot extract oxygen from water. Every dive is bounded by breath. In deep, open water, this is manageable. Ascent angles are flexible, and surfacing can happen almost anywhere. In shallow reef systems, however, depth gradients compress. Coral heads rise close to the surface. Sandbanks form barriers. Tidal shifts expose and submerge obstacles unpredictably. The turtle's path upward becomes constrained, and so it reuses the same gaps, channels between coral bommies, sloping reef edges, sand corridors that allow a clean, efficient ascent without scraping shell or flippers. These are surface lanes. From above, they are invisible. From within the system, they are essential infrastructure. The problem is that humans and boats learn these lanes too, without realizing it. Snorkelers tend to drift where turtles appear most often. Kayaks idle in calm channels. Boats slow near reef edges where turtles surface regularly. What feels like a lucky encounter is often repeated use of the same narrow vertical routes. Over time, these spaces become crowded, not because the reef is busy everywhere, but because activity concentrates in predictable places. For the turtle, this predictability is a liability. Green sea turtles evolved in oceans where threats came from below or behind, large sharks that ambushed from depth. Their defenses reflect this history: thick shells, strong downward swimming power, and the ability to hold breath for extended periods when resting. What they did not evolve for is congestion. In tight, shallow environments, the turtle's greatest strengths, size, shell, inertia, become constraints. Turning radius increases. Acceleration drops. Escape angles collapse. This is where risk accumulates, quietly and consistently. A turtle rising along a familiar lane expects open water at the top. When that space is occupied by swimmers, hulls, ropes, or other turtles, the margin for error vanishes. A startled turtle does not dart sideways like a fish. It powers forward or downward, often into obstacles. Shells scrape coral. Flippers strike rock. In extreme cases, turtles collide with boats or become entangled in lines that intersect their ascent path. None of this requires malice or panic. It is a mechanical consequence of large bodies moving through tight corridors designed by habit, not choice. Shallow reefs amplify this danger further through crowding. Multiple species share the same compressed space. Turtles feeding on seagrass, rays buried in sand, fish darting between coral heads, humans hovering mid-water. Everyone is operating within meters of everyone else, often with limited visibility and reduced reaction time. Small mistakes propagate quickly. A snorkeler kicks hard to regain balance and stirs sediment. Visibility drops. A turtle surfaces into turbulence and veers. Another swimmer drifts unknowingly into its path. What began as a calm, gentle interaction shifts into a cascade of adjustments, each one narrowing options for the next movement. From the turtle's perspective, the shallows are not peaceful. They are busy. This is why turtles are often seen resting under ledges or wedged against reef structures during the day. These resting corridors are not chosen for comfort alone. They provide predictable cover and reduce the need for constant maneuvering. A resting turtle minimizes surfacing trips, conserving oxygen and avoiding congested lanes. But even these refugees are close to human traffic, especially in popular snorkel zones. A turtle flushed from rest by disturbance must re-enter the surface lane system abruptly, often without the gradual ascent it prefers. Biologically, green sea turtles are optimized for efficiency, not agility. Their metabolism supports long-distance migration and herbivorous feeding, not rapid acceleration. Their muscle structure favors endurance over burst speed. In open water, this is sufficient. In tight spaces, it becomes a vulnerability. The turtle cannot simply get out of the way when something unexpected blocks its route. It must commit to a path and power through. This is where the environment becomes the real hazard. Unlike predators that actively target turtles, shallow reefs create passive risk through geometry and repetition. The same lanes used for safety become choke points. The same calm waters that invite humans reduce escape options. The same predictability that allows turtles to thrive in stable systems becomes dangerous when those systems fill with moving parts. It is tempting to frame turtle encounters as moments of tranquility in otherwise dangerous oceans. But this framing misses the underlying reality. Shallow reefs are not safe zones. They are high-density intersections where biology, physics, and human behavior overlap tightly. The turtle is not the threat. The traffic is. This is why conservation guidelines emphasize distance and positioning rather than avoidance. Giving turtles space is not about protecting humans from turtles. It is about preserving the integrity of those surface lanes, keeping escape routes open, reducing forced maneuvers, and allowing animals to move according to the patterns that have kept them alive for millions of years. When those patterns are disrupted, stress rises, injuries increase, and the system frays. Seen through this lens, the green sea turtle becomes a visual anchor for the entire episode's message. It embodies calm, but moves through a landscape defined by constraint. It appears harmless, but travels through spaces where small mistakes cascade. It reminds us that danger in the wild is not always an aggressive act. Sometimes it is congestion. Sometimes it is predictability. Sometimes it is the quiet pressure of too many bodies sharing too little room. As the episode closes, the lesson sharpens. Shallow reefs are not simplified versions of the ocean. They are compressed versions, dense with life, habits, and intersecting paths. They demand more awareness, not less. The turtle gliding past is not an assurance of safety. It is evidence that you are standing in a corridor that matters. In Australia's coastal ecosystems, the most misleading moments are the calmest ones. Slow animals, clear water, gentle light. These are the conditions where attention drifts and assumptions take over. The green sea turtle does not warn you away. It does not attack. It simply moves again and again through the same narrow lanes that have always worked, until something blocks them. And that is the real message. Not that turtles are dangerous, but that shallow reefs are busy, tight, and mistake-driven environments. The danger is not who you meet there. It is how little room there is to be wrong. In Australia's coastal waters, danger often arrives not with speed or spectacle, but with misunderstanding. Sea snakes glide through reefs, seagrass meadows, and murky estuaries with an ease that reads as calm, even gentle. Their movements are slow, deliberate, and fluid, shaped by a life spent conserving oxygen and navigating complex underwater terrain. To human eyes, this calm is deceptive. It looks like tolerance. It looks like approachability. And in tight spaces, it becomes the precondition for one of the most consistent human-caused bite patterns in the marine world. Most sea snake incidents do not begin with fear. They begin with intent. Someone sees a snake moving slowly near the surface or resting along the bottom and decides it needs help, documentation, or control. The motivations vary: curiosity, bravado, a photo opportunity, or the assumption that a slow animal must be weak. But the mistake is always the same. The person steps into the snake's escape geometry without realizing it. A hand enters the water. A body blocks a corridor. A net tightens. The environment collapses inward, and what was once an open three-dimensional world becomes a trap. Sea snakes are not built for confrontation. Evolution pushed them in the opposite direction. Their bodies are laterally flattened for swimming efficiency, their lungs elongated to manage buoyancy and oxygen storage, their scales adapted to reduce drag. Many species can absorb oxygen directly through the skin, allowing long, energy-efficient dives. All of this points to one core survival strategy: move away, not fight. In open water, this works beautifully. A sea snake that senses disturbance simply slips past coral heads, disappears into seagrass, or sinks into deeper water where pressure and distance solve the problem. The problem arises when distance is removed. Trapped space encounters are fundamentally different from open water encounters. In reef crevices, shallow corners, tide-restricted pools, fishing nets or human-made barriers like boat hulls and pontoons, the snake's primary defense, escape, fails. This is not immediately obvious to humans because the water still looks open. But from the snake's perspective, escape routes are three-dimensional and precise. A body blocking a channel, a hand hovering near the head, or tension on a net line collapses those routes into dead ends. At that moment, the snake is no longer avoiding you. It is responding to entrapment. This distinction matters because sea snake venom evolved under very specific pressures. These snakes primarily hunt fish, often in complex reef structures where prey can be slippery, fast, and difficult to hold. Their venom is optimized for rapid immobilization, potent neurotoxins that shut down muscle control efficiently, preventing prey from escaping into crevices. In human terms, that potency is severe, even though the snakes themselves are not aggressive by nature. The venom is not meant for defense against large animals, but when deployed defensively in close quarters, its effects are no less real. Crucially, sea snakes are reluctant to bite unless forced into this corner. Many documented interactions involve prolonged contact where the snake repeatedly attempts to move away, changing direction, slowing down, or freezing entirely. These behaviors are misread as docility. In reality, they are de-escalation attempts. The snake is waiting for an exit to open. When humans continue to handle, restrain, or pose with the animal, they remove that final option. At that point, the bite is not an attack. It is the last remaining tool. This is why grabbing is such a powerful trigger. Hands are not neutral objects underwater. They are large, warm, and fast-moving compared to the snake's sensory expectations. When a hand grips the body or tail, it creates two simultaneous threats: physical restraint and proximity to the head. In snake behavior, restraint overrides almost all other considerations. A restrained snake cannot flee. The nervous system shifts instantly from avoidance to defense. In sea snakes, this transition can be subtle. There is no dramatic strike posture, but the outcome can be immediate. The concept of the trap zone helps explain why these incidents cluster in specific environments. Reef flats at low tide compress vertical space. Nets and fishing lines create invisible barriers that entangle without warning. Shallow coves funnel movement into corners where snakes surface to breathe but cannot dive deeply. Even human bodies can become part of this geometry, blocking paths unintentionally. In all of these scenarios, the snake's perception of space collapses. It is not reacting to a human as a predator. It is reacting to the loss of motion itself. From an ecological standpoint, this sensitivity to entrapment makes sense. Sea snakes evolved in environments where getting stuck can be fatal. A snake caught in a crevice without oxygen access, pinned by a predator, or entangled in debris has limited time to resolve the situation. Fast escalation is adaptive. Waiting too long costs oxygen, energy, and life. Defensive bites in trapped spaces are therefore decisive, not gradual. The snake does not test with warning nips. It commits fully when the line is crossed. What makes this dangerous for humans is that the line is often crossed unintentionally. People believe that calm handling equals safety, that slow animals are tolerant animals. But tolerance in wildlife often means something else entirely. It means restraint. It means the animal is choosing not to escalate because it believes escape is still possible. When humans mistake restraint for permission, they misjudge how close the system is to failure. Another layer of misunderstanding comes from how rare bites actually are relative to exposure. Sea snakes are abundant in Australian waters, especially in northern regions, and encounters are common among divers, fishers, and snorkelers. The vast majority end without incident precisely because people do not interfere. The statistical pattern is clear. Bites cluster around handling, harassment, or forced proximity. They are not random. They are not ambushes. They are predictable outcomes of spatial pressure. This predictability is what makes the lesson here so important. Sea snakes are not dangerous because they are aggressive. They are dangerous because their venom is powerful and their tolerance for entrapment is low. Respecting that boundary does not require fear. It requires spatial awareness. Give the snake a clear exit, and it will take it. Remove that exit, and you inherit the consequences of a system that evolved to resolve traps decisively. There is a quiet irony in how often these animals are described as friendly in popular narratives. The descriptor usually comes from divers who have allowed snakes to approach or circle them without incident. What those divers are actually witnessing is a perfect alignment of conditions: open water, no restraint, and mutual non-interference. The moment any one of those variables changes, the dynamic shifts. Understanding that fragility is key to safe coexistence. Seen through this lens, sea snakes are not anomalies, but case studies in escalation physics. Behavior is shaped less by intent than by geometry. When space is abundant, conflict dissolves. When space collapses, biology resolves the problem quickly. This is not a moral judgment by nature, it is an efficiency rule. The broader takeaway extends beyond sea snakes. Many marine animals operate under similar logic, where escape is prioritized and defense is reserved for moments of confinement. Humans, with our tendency to reach, grab and block, accidentally create the exact conditions that trigger defensive systems we then label as dangerous. The sea snake does not break the rules of the ecosystem. It follows them precisely. In Australia's coastal waters, where reefs, tides and human activity intersect, understanding those rules is the difference between awe and injury. The sea snake asks for very little: space, patience, and an open path away. When it receives those, it disappears without drama. When it does not, the outcome is not random or malicious. It is the predictable result of a trapped animal solving the only problem left to solve. The tide pools along Australia's rocky coast look harmless at first glance. Shallow bowls of clear water trapped between shelves of stone, warmed by the sun and crowded with color. Algae glows green against basalt. Tiny fish flicker like sparks. Shells gleam. This is where people slow down, crouch, lean in, and let curiosity take over. It is also where scale lies to you. In tide pools, danger does not announce itself with size, speed, or noise. It announces itself with pattern, timing, and restraint, and the blue-ringed octopus is one of the cleanest demonstrations of that rule anywhere in the animal world. The first mistake almost everyone makes here is visual. Bright colors are subconsciously read as decoration, novelty, or fragility. A creature small enough to fit in a palm, patterned like jewelry, triggers the same instinct as a seashell or a tide pool starfish. Hover closer, point, touch. The logic feels harmless. If it were dangerous, it would be large. If it could hurt you, you would see teeth, spines, or speed. That assumption works in many ecosystems. It fails completely in shallow marine environments where chemistry and nerve physiology matter more than muscle, and where a defensive bite does not need force, only access. The blue-ringed octopus does not hunt humans. It does not patrol aggressively or chase intruders. Most of the time, it wants to be invisible. Its natural state is camouflage so complete, it disappears into rock and sand, its skin texture adjusting to match pits, ridges, and shadows. In that state, you can kneel inches away and never notice it. The problem begins when invisibility fails, when a shadow falls too long, when fingers probe a crevice, when a rock is lifted and the animal is suddenly exposed with nowhere to retreat. That is when the warning appears. The rings are not decoration. They are not a display meant to impress or intimidate from a distance. They are a neurological flare. When the octopus is stressed, specialized skin cells flash electric blue in high contrast against its yellow-brown body. This is not slow coloration, like a cuttlefish shifting mood. It is rapid, high-visibility signaling triggered by threat. The message is precise and narrow. You are too close, and escape routes are closing. In evolutionary terms, this display exists because it works, because predators that ignored it did not get a second chance to learn. Humans, unfortunately, often misread the signal in the worst possible way. The rings are beautiful. Cameras come out. Hands move in closer. Some people try to lift the animal just for a second, assuming the bite would be mild if it happens at all. But the blue-ringed octopus does not rely on pain as a deterrent. Pain teaches. Its venom does not teach. It shuts systems down. The toxin involved, tetrodotoxin, is among the most potent neurotoxins found in nature. It does not burn tissue or cause swelling. It blocks sodium channels in nerves and muscles, preventing electrical signals from passing. In practical terms, this means voluntary movement stops. Breathing muscles fail. Consciousness can remain intact while the body becomes unresponsive. There is no anti-venom. Survival depends on rapid respiratory support until the toxin is metabolized. The margin between a recoverable incident and a fatal one is narrow, and in remote coastal areas, time is not on your side. What makes this especially dangerous in tide pools is how bites occur. The octopus does not need to lunge. It does not need to open wide. Its beak is small, designed to pierce crabs and mollusks, and its bite can feel like nothing more than a pinprick, or nothing at all. There may be no immediate pain to trigger alarm. People sometimes realize something is wrong only when their fingers feel weak, their speech slurs, or their chest feels heavy. By then, the interaction is already over. The animal has defended itself and retreated. The consequence unfolds silently in the human nervous system. From the octopus's perspective, this is not aggression. It is the final step in a tightly constrained decision tree. First, hide. Second, signal. Third, only if trapped, handled, or restrained, bite. In the wild, most predators never push past step 2. Humans do, because hands bypass the warning logic evolution built. A hand can grab, block exits, and apply pressure in ways jaws usually cannot. In tide pools, hands are faster than teeth, more precise than mouths, and far more dangerous to small animals. The blue-ringed octopus's venom is the evolutionary answer to that kind of threat. There is a deeper ecological lesson here, one that extends beyond this species. Tide pools are compressed ecosystems. Space is limited. Retreat options are few. Many organisms living there evolved chemical defenses precisely because they cannot rely on escape. Unlike open water, where speed and distance can resolve encounters, tide pools force confrontation. That pressure favors toxins, warning coloration, and last resort weapons that act instantly. The blue-ringed octopus is not an outlier. It is simply one of the most extreme expressions of that logic. This is why the core rule matters. In tide pools, hands get you punished faster than teeth ever could. Teeth announce intent. Teeth give time to react. Hands move quietly, confidently, and without the visual cues animals evolved to read. To a tidepool animal, a hand is an unpredictable trap, able to lift, pin, or block escape in seconds. When people violate that boundary, they are not being attacked. They are being responded to. There is also an uncomfortable irony in how often this species is encountered during moments meant to be calm. Families exploring at low tide, snorkelers resting between dives, tourists pausing to admire harmless marine life. The blue-ringed octopus thrives in exactly these conditions: shallow, sheltered areas with abundant prey and crevices for cover. Its danger is not paired with hostility or drama. It is paired with stillness, with patience, with the kind of quiet presence that rewards distance and punishes contact. Understanding this animal properly requires reframing what warning means in nature. Not all warnings are loud. Not all consequences escalate gradually. Some systems operate on thresholds, not ramps. The blue-ringed octopus does not injure you more because you stayed longer. It injures you fully the moment the line is crossed. That design is not cruel or excessive. It is efficient. It minimizes struggle, energy expenditure, and repeated conflict. From an evolutionary standpoint, it is nearly perfect. The tragedy is that humans often mistake restraint for safety. Because the octopus does not bite immediately, people assume it will not bite at all. Because it is small, people assume it cannot kill. Because it is beautiful, people assume it is benign. Each assumption stacks toward the same error. The environment does not correct that error gently. In the end, the blue-ringed octopus is not a story about venom. It is a story about scale blindness, about how human intuition fails in ecosystems governed by chemistry rather than force. It is a reminder that warning signals are not invitations to get closer, and that beauty in nature is often paired with boundaries that are absolute. In Australia's tide pools, nothing illustrates that truth more cleanly or more unforgivingly than a creature small enough to cradle, flashing a warning you are meant to respect, not test. In Australia's shallow coastal waters, the sand itself lies. It looks smooth, pale, undisturbed, an empty surface that suggests safety through simplicity. People wade in with relaxed posture, eyes forward, attention drifting toward the horizon or the shoreline rather than down at their feet. This is the same psychological error that happens along riverbanks and estuaries. Calm water lowers vigilance. The reef equivalent of murky river edges is pale sand, and beneath it waits an animal that is neither hunting nor hostile, but perfectly positioned to turn surprise into injury in a fraction of a second. Stingrays are not ambush predators of people. They do not patrol shallows looking for conflict. Most of the time, they are barely present at all, buried beneath a thin layer of sand with only eyes and spiracles exposed, bodies flattened and still. This posture is not laziness. It is a carefully tuned survival strategy that balances energy conservation, camouflage, and respiration. The ray's body pumps water over its gills while buried, filtering oxygen without stirring sediment, remaining effectively invisible to both predators and prey. From above, there is nothing to signal danger, no movement, no silhouette, no sound. The problem begins when invisibility meets weight. Unlike animals that rely on teeth or pursuit, stingrays are built around a reflex weapon designed for last resort defense. The tail spine is not a stinger in the insect sense. It is a serrated, backward-facing barb connected to venom glands and driven by powerful reflexive muscle contractions. It is not aimed. It is not chosen. It fires when the animal is startled, compressed, or stepped on. And in shallow water, surprise happens fast. Most stingray injuries occur when someone steps too close or directly onto the animal's disc. The contact is sudden, heavy, and unavoidable from the ray's perspective. A foot comes down, pressure spreads across sensitive tissue, and the nervous system responds instantly. The tail whips upward in a defensive arc that has evolved to strike predators attacking from above. The timing is automatic. There is no assessment phase. The system assumes the worst because, in evolutionary terms, hesitation would be fatal. This is why escalation is so rapid. Stingrays do not warn in advance. They do not flash colors or posture. Their primary warning is absence, the expectation that predators and large animals will pass overhead without contact. When that assumption fails, the response is immediate and proportional to the force applied. A gentle brush may result in the ray bolting away in a cloud of sand. A direct step compresses the body and triggers the full defensive reflex. Shallow water amplifies this risk in multiple ways. Space is compressed vertically, limiting escape depth. Human movement becomes clumsy as waves push against legs and balance shifts unpredictably. People move faster to compensate, lifting feet higher and planting them more forcefully. Every step becomes heavier, less controlled, and less informed by visual feedback. For the ray beneath the sand, this feels like a predator attack delivered without warning. The irony is that stingrays are among the most peaceful large animals in these environments. They feed on mollusks, crustaceans, and buried invertebrates, using electroreception to detect tiny electrical signals beneath the sand. Their hunting behavior is slow, deliberate, and methodical. They excavate gently, leaving subtle feeding pits that mark their passage long after they move on. None of this aligns with aggression. None of it prepares them for sudden vertical force. From an ecological perspective, burying in sand solves many problems at once. It hides the ray from sharks. It stabilizes body temperature by buffering against surface heat fluctuations. It allows efficient respiration without constant swimming. But it introduces one unavoidable vulnerability: being stepped on. The venomous spine exists precisely because this risk cannot be eliminated through camouflage alone. It is a mechanical insurance policy against surprise contact from above. Understanding stingray injuries requires reframing them not as attacks, but as collisions between two incompatible movement systems. Humans move through shallow water as if it were land, trusting their feet to test space. Stingrays experience the same space as a ceiling that should never collapse. When it does, the reflex weapon fires before cognition ever enters the loop. This dynamic mirrors the logic of riverbanks and crocodiles in a subtler way. Just as murky water hides a crocodile's position and collapses reaction time, sand hides reef hazards and removes visual confirmation. In both cases, the environment masks risk until proximity becomes unavoidable. The difference is scale and intent. Crocodiles actively hunt. Stingrays do not. Yet the outcome, injury triggered by sudden contact, can feel equally abrupt to the person involved. There is also a misconception around the so-called stingray shuffle. Shuffling feet through sand rather than stepping lifts sediment, sends vibrations, and gently nudges rays out of the way before full body weight comes down. This works not because rays are timid, but because it preserves their ability to flee. The moment a ray feels lateral disturbance without compression, it swims off. Compression removes that option. The difference between those two movements, shuffle versus step, is the difference between de-escalation and reflex defense. Physiologically, the stingray's response is efficient and limited. The spine is not used repeatedly. It is a high-cost structure that can break or become embedded, leaving the animal vulnerable afterward. This further underscores how last resort the behavior is. A ray that deploys its spine pays a price. It does so only when the alternative appears worse. From the animal's perspective, a sudden heavy force from above signals imminent crushing or predation. There is no evolutionary benefit to restraint in that moment. Human injury, then, is a side effect of a system never meant to engage with us at all. Stingrays evolved alongside sharks, large bony fish, and marine mammals, not barefoot primates wading casually through their resting grounds. The overlap is accidental, but the consequences are real. Pain, tissue damage, and risk of infection follow not because the ray intended harm, but because its defensive design prioritizes immediacy over discrimination. Seen clearly, the stingray is not a villain of the shallows. It is a reminder that flat, quiet environments often hide the most finely tuned reflexes. In Australia's coastal ecosystems, sand is not empty space. It is active habitat, layered with animals that rely on concealment and instant response rather than pursuit or display. When humans forget that, escalation happens fast. The lesson here is not fear, but awareness. Look down. Move deliberately. Understand that shallow water is not simplified water, it is compressed water, where reactions must be faster because margins are thinner. Stingrays do not want conflict. They want to remain unseen. When that invisibility is broken by weight instead of warning, the environment resolves the mistake immediately. In the end, the stingray's story is not about venom or injury. It is about startle physics, about what happens when pressure meets reflex in a space too small for negotiation. The sand does not advertise what it hides. And in that silence, evolution has already decided how surprise will be handled, long before any human foot ever touched the bottom. In the shallow margins of Australia's reefs and lagoons, danger does not rush, stalk, or chase. It waits. Water thins to ankle depth, sunlight breaks into fragments across sand and rubble, and people relax. This is the psychological trap of shallow water. It feels transitional, a place between land and ocean where the rules soften. Waves are smaller. Visibility is high. Movement slows. The sense of threat drops before the environment ever does. And embedded within that complacency is one of the most perfectly engineered defensive animals on the planet, built not to attack, but to punish a single careless step with mechanical precision. The stonefish does not hide near the bottom. It is the bottom. Its body is shaped like collapsed terrain, uneven, knuckled, pitted, covered in skin that mimics algae, encrusting sponge, sand grains and reef debris so convincingly that even experienced divers miss it. This camouflage is not decorative, it is structural. Skin flaps imitate decaying weed. Coloration breaks up outline rather than matching a single background. The fish does not look alive because, evolutionarily, looking alive would be a liability. Anything recognizable as a fish draws attention. Anything mistaken for rock gets stepped on. That is not a failure of design. That is the point. Stonefish occupy precisely the zones humans underestimate most: shallow reef flats, tidal channels, murky estuaries. sandy-bottomed lagoons where visibility fluctuates and footing matters more than navigation. In these environments, people stop scanning for predators and start scanning for balance. Eyes lift forward instead of downward. Attention shifts from biology to footing mechanics. How slippery the rock is, how strong the surge feels, how fast the water is moving past the ankles. This is where the stonefish wins without moving. The loss is not about speed or surprise. It is about pressure. Unlike venomous animals that rely on a bite or strike, the stonefish's weapon system is passive until activated by force from above. Along its dorsal ridge sit thick, rigid spines connected to venom glands, each spine encased in a sheath that ruptures under compression. The moment weight comes down, the system engages. The harder the pressure, the deeper the spines penetrate. This is not incidental. It is a mechanical logic tuned to one specific threat: being stepped on. A footstep is not a glancing contact. It is a vertical load. Hundreds of kilograms of force concentrated through bone and muscle, transferred through skin, soul and water to whatever lies beneath. In most animals, being stepped on is catastrophic, regardless of defense. In the stonefish, being stepped on is the trigger that completes the weapon cycle. Pressure drives the spines in. Penetration squeezes venom upward through ducts. There is no hesitation, no aiming, no decision-making required. The fish does not choose to envenomate. The environment does it for them. This is why the injury is so severe. Stonefish venom is not injected delicately. It is forced into tissue by mechanical compression, often deep into muscle. Pain arrives immediately and overwhelmingly, described as crushing, burning, electric. Pain that escalates rather than fades, because venom continues dispersing through tissue under residual pressure and movement. The body reacts violently: swelling, vascular constriction, systemic stress responses. Even when treated promptly, the experience leaves a lasting impression because the venom evolved to make one thing unforgettable: don't step here again. Yet despite the severity of the outcome, the stonefish is not an aggressive animal. It does not hunt large prey. It does not chase intruders. Most of its time is spent motionless, conserving energy, ambushing small fish or crustaceans that drift close enough to inhale. Its camouflage serves two purposes at once: concealment from predators above and invisibility to prey below. The venomous spines exist because hiding at ground level carries a unique risk. When concealment fails, escape is impossible. There is no burst of speed, no evasive maneuver that works under a foot. Defense has to be instant, decisive, and proportional to the threat. From an evolutionary standpoint, this is elegant. The stonefish does not waste venom on minor contact. A brushing hand, a grazing fin, a shadow overhead, none of these activate the system fully. Only pressure does. Only a step. The fish's survival strategy is calibrated not to curiosity, but to weight. That tells you exactly what kind of predator shaped it over millions of years: large, blunt, downward-moving animals that do not bite first. Humans fit that profile perfectly. There is also a subtle ecological irony here. The same features that make shallow water appealing to people, easy access, warmth, visibility, are the features that make it a high-risk zone biologically. Shallow reef flats are nurseries. They are feeding grounds. They are transitional spaces packed with organisms that cannot flee quickly because the water itself limits movement. Defense replaces escape. Chemistry replaces speed. And the stonefish represents the extreme end of that continuum. Behaviorally, the fish gives almost nothing away. It does not flare spines preemptively. It does not advertise its danger the way some venomous animals do. That restraint is often misinterpreted as passivity or harmlessness, when in fact it reflects confidence in the system. Warning displays evolve when animals need predators to stop before contact. The stonefish expects contact and punishes it. That tells you how often camouflage alone succeeds. Most predators never find it. Those that do rarely survive the lesson. Humans, however, are not predators in this context. They are accidental participants in a defense system never meant for curiosity-driven movement. That mismatch is what makes stonefish injuries so common in exactly the places people feel safest. Reef shoes reduce risk, but they do not change the underlying rule. If you stop scanning the bottom, you are outsourcing your safety to luck. Understanding the stonefish properly requires abandoning the idea that danger always moves toward you. Some danger waits for you to move wrong. The stonefish is not a threat in open water. It is not a threat if you swim above the substrate. It becomes a threat only when your behavior aligns perfectly with its defensive trigger. That specificity is why it has survived unchanged for so long. The system is precise, energy efficient, and brutally effective. There is a deeper lesson embedded here about how evolution solves problems. Instead of speed, the stonefish evolved structure. Instead of aggression, it evolved inevitability. Instead of constant readiness, it evolved a pressure-activated switch. This is not a creature optimized for dominance, it is optimized for being left alone. And in that sense, its venom is not a weapon of conquest, but a boundary enforcement tool, designed to make one message unmistakably clear across species lines. In Australia's shallow waters, where reef meets footstep and curiosity meets complacency, the stonefish stands as proof that the most dangerous systems are often the quietest. Not because they want to harm, but because they have no room to retreat. When you understand that, the environment reads differently. The bottom is no longer background. It is active, contested space. And every step becomes a decision, one that evolution has already solved from the stonefish's side. The fish does not need to see you. It does not need to react. It only needs you to forget for a second that shallow water is still wild.